As a background, so in spite of the development of many kind of ICT such as cell phone or SNS or something like that, the face-to-face conversation is still the most frequent mode of communication. The technologies that makes remote communication as realistic as face-to-face communication have huge advantages, such as reducing labor or travel costs required for the face-to-face decision making. However, the planar display, which you may see right now, cannot accurately transmit non-verbal information, which plays an important role in communication. It is reported that the turn taking in multi-party Model 3 conversation is adjusted by eye gaze or gesture. The problem of accurate gaze transmission is because of the Mona Lisa effect. The Mona Lisa effect means that from the frontal facial image shown in the left side of the figure invokes eye contact perception from any angle, regardless of the observation direction. Like both A and B feel the gaze. And meanwhile, no frontal facial image doesn't invoke eye contact perception, regardless of the observation direction from any angle, such as A and B, which both don't feel their gaze. So many studies have tried to eliminate this Mona Lisa effect by using the volumetric display, such as the multi-view 3D display or face shape display. However, these displays needed actuated mechanisms are thus cause mechanical noise and maintenance issues. So it is also reported that the curved display, such as shown in the picture, can transmit eye gaze more accurately than a planar display. And we also believe that for the practical video conference system, the convenience also needed. So high versatility is needed because unspecified users might participate in conference in such as company or schools or laboratories. And also, low manufacturing cost and high reliability is also needed for its convenience. So the fewer the driving mechanisms in the system, the lower the risk of failure and manufacturing cost. And however, mechanisms are normally needed in the conference system to turn the face by 90 degrees to look at participants in the table meeting. But these mechanisms are not necessary on the displays like shown in the figure, which is a vertical axisymmetric surface of revolution-shaped display. Yes, which can express horizontal head rotation only with changes of image. And we also believe that the similarity of the display face to the real face is also needed. The interlocutor of the video conference system used to talk or will talk face to face with the partner, with the person at least once. So if the display facial image is not like a real face, which was seen before and after, so it can be difficult for the users to recognize the image as interlocutor. So it has been reported that we identify the interlocutor, who is that, by the overall arrangement of the parts and contour of the face, such as nose and mouth as eyes or jaw contours. So a display that can show it naturally from any angle is necessary. So this elimination of the Mona Lisa effect and the convenience for practical video conference system and the similarity of the displayed face to the real face. These three characteristics is required for practical video conference system. So we propose TEllipsoid, which is an ellipsoidal display for video conference system that has a curved and vertical axisymmetric surface and the affinity with human face. So we call it as the TEllipsoid, The main mechanism is bottom insert small projector projects the facial image onto this ellipsoidal screen using the convex mirror. Lastly, we made a prototype in virtual reality environment, which was made with Unity and built on Oculus Quest. The facial image was generated by concatenating the cropped facial images, such as center part of each photos, cropping this photo and such like this, and concatenating like this. And this each photo taken from the movie, and this generated facial image will be inverse cylindrical projected on the screen. And the screen shape was designed from the average dimensions of the face of young Japanese males. We also implemented the gaze representation method we put the eyeballs models onto the virtual ellipsoid screen. We put the eyeball models gaze at the target position by turning the popularity axis towards the target. And we then project the eyeballs onto the screen surface using along the popularity axis using the parallel projection. With this method, the geometry looks consistent with eyeball models, when it was gauged from the target position. And we also made the prototype device, which screen was fabricated with 3D printer, and the projector was a laser projector, and the convex mirror is a spherical mirror, and the facial image for the projection is generated by the optics set up in Unity virtually, which is equivalent with the real device. For this prototype device, we enlarged the lower part of the screen. We modified the screen shape to improve the geometries of the nose and mouth and the naturalness of the profile. And we filled the neck part of the facial image with black to express the contour of the jaw. And this black fill, shape of black fill was adjusted, make both frontal face appear slender and the contour of the jaw appear natural. And this improvement also has the potential to evoke the wall-lasting illusion. For the virtual reality prototype, we did an experiment one, which objective is investigating whether we can perceive eye contact only from a specific direction. And we want to acquire the relationship between gaze angles and observation angles, which gives the perception of eye contact. For the condition, the participants are 11 people who stand to observe the display from 1 meter away in the virtual reality environment. So we allocated the gaze angle and the observation angle like this. As a procedure, the participant indicates whether the display gazes at them or not. For each combination of the gaze angle and observation angle in total 77 stimulus, which was presented randomly for 5 seconds by pressing button or yes or no. So firstly, this is the result. The number of who perceives the number of the participant who perceives eye contact for each stimulus. The bigger the gaze angle, the bigger the observation angle which eye contact was occur. However, the gaze angle and the observation angle were not always consistent. So we also did a similar experiment in real device, which objective is acquire the precise gaze angle for the fixed observation angle, some observation angle, which participants strongly feel eye contact. So the condition is 11 participants who observes the device from 1.5 meter away in the dark room, which the viewpoint was matched between the participant and the device. As a procedure, the observation angle affixed. These 7 observation angles are presented randomly. For each observation angles, the participant adjusts the gaze angle to the place they feel eye contact strongest by pressing buttons to change the gaze angle by fixed values 2 or 0.5 degrees. This projection blinked for 0.5 seconds each time the button was pressed. As a result, the gaze angle for which the strongest eye gaze was perceived for each observation angle was acquired. The result is similar to result 1. We conclude that a facial image gazing front evokes the perception of eye contact only from front, and the facial image not gazing front evokes the perception of eye contact from a specific range of observation angles. Therefore, we conclude that Mona Lisa effect was eliminated. However, multiple people are likely to perceive eye contact from a single gaze representation when gaze angle is approximately 8, 16, 24 degrees. So further investigation is required. So we did the experiment 2.2, which objective is investigating the range of observation angle where participants still feel eye contact for each gaze angle, which was acquired in experiment 2.1. Condition is same as 2.1, and the procedure is the participants change the observation angles in one direction from the strong gaze representation, which was acquired in last experiment, to the place in which they no longer face eye contact. These adjustments were made to the left and right, and every observation angle presented randomly. So in total, 14. So the range of the observation angles, which participants perceived they still perceive eye contact with from the strongest gaze representation. So angular range width from the given observation angle was 38.5 degrees on maximum. So accurate gaze transmission is available in conferences when the angular distance of the adjacent participant is more than 38.5 degrees. And has been reported that the range of gaze angle where mutual gaze occurs has no clear border about Gaussian probability distribution. So narrower psychologically significant range can be derived. And we also did experiment 3, which is impression evaluation, which we want investigate whether the participant can recognize the display image as a remote participant, and investigate how they feel about the image. We did this experiment with 11 people, for each participant we do the participant rated this display with the visual analog scale such as shown in right. So participants were allowed to change gaze angle in a dark room. So each mark of this visual analog scale was converted into the ratio as the distance from the left end against the total length of the line. So for the first question, the average of the ratio were almost neutral. So the impression of display face are almost neutral. For the question, second question is the result is closer to easy to recognize. So it means more than half of the participants can easily identify the facial image as the interlocutor. So our method provides a high level of identity between the display and real face. This is a conclusion of our research.